Hello, Krakow. My name is Andrey. I come from Berlin, where I work at SoundCloud as a front-end engineer. So this talk is going to be about WebGL in Elm. We're not using WebGL at SoundCloud, but I have a 20% SAT time that I spent on working on Elm for internal tooling, and also SoundCloud supports me in hosting Elm meetup in Berlin. This talk is not about work. This is something that I have been doing for fun, and it's called Bringing the Fun to Graphics Programming. So I've been writing front-end mainly in JavaScript for about 10 years now, and every time I want to start something new, I face this JavaScript fatigue where I spend a lot of time figuring out what is the current state of JavaScript, which libraries I should use, what tooling should I configure, and it takes so much time that it has become very difficult to start something and see the results on the screen. So something like this. And Elm was a breath of fresh air for me because I could easily prototype some ideas and see them on the screen immediately. Elm also allowed me to try something new in the browser API, which was WebGL. And eventually I ended up being a maintainer of WebGL library in Elm. So how many of you have tried WebGL? Awesome. And how many of you tried Elm? Cool. So I learned WebGL through Elm. So I first learned Elm, and then I learned WebGL through the library. So in this talk, we are going to cover why WebGL in Elm. Then we will cover the basics of the rendering pipeline, and the last part is going to be examples and demos. So why WebGL in Elm? My path into WebGL was through making a game. When I was working at Lambda, we created a game called Elm Street 404 with my former colleagues. And we were exploring the way to render graphics in this game. So we had some tools, some things to try. First, we rendered it with HTML package using a bunch of divs, and soon we've discovered that this thing was performing slow on mobile devices. There is another package called Elm Graphics that implements Canvas API in Elm, but that one didn't have an API to render sprite sheets, which we needed for animations. And there is also a way to render it with SVG, but our game was a raster game and not a vector game, so SVG was not considered. WebGL, on another side, performs much faster than DOM for many elements on the screen. It provides us an access to fast parallel computations on GPU. With WebGL, we also have fine-grained control over rendering, so we could achieve rendering sprite sheets, for example. However, WebGL itself has a steep learning curve. Its API is very complicated if you look at it in documentation. WebGL in Elm, however, is a very nice way into learning WebGL. It offers a declarative API, the one that you may be familiar when working with Elm or React, where you declaratively define things that you want to see on the screen, and then the library will handle everything for you. So you're dealing with triangles instead of native arrays. Also, Elm has a library for linear algebra computation, so you don't have to worry about that. So you have convenient way of dealing with vectors and matrices. And the most controversial feature of Elm is that Elm language itself has a baked-in support for shaders. So you can write a GLSL code block in your Elm program, and this GLSL program will be compiled and linked automatically for you. And more to that, what Elm does, it also derives a type signature for your shader. So when you write GLSL code, it is parsed and type signature is built for your Elm code, so that it makes sure that you're passing correct inputs to shaders. Because if you didn't have this and you messed something up, then you would see a white screen of death. These are the benefits of using WebGL in Elm, and the question you may ask is how to get started. So first of all, you have to learn about the graphics pipeline. So here it is on the scheme. The first thing you do is you define a mesh. And mesh, you can think about it as a bunch of triangles, where on each vertex of triangle you can attach any information that you want. So this can be position on the screen or position in 3D space, texture coordinates, or color, like in this example. Then the first thing that is executed is a vertex shader. Vertex shader receives each vertex of each triangle, and its job is to calculate where this thing should be on the screen. So it returns gel position. It also can return varyings, which is a way to pass information to the fragment shader. A fragment shader, for the simplicity, you can call it a pixels shader. So it is called for every pixel within triangle. And it receives interpolated value of varyings. So in our case, you see that this triangle is filled with colors that are interpolated from RGB colors. And the output from fragment shader is just the color. What color should this pixel be on the screen? And the last bit is uniforms. And uniforms are global constants that allow you to configure the scene. So this can be, for example, camera or projection matrix, or a texture, so that you can look up for a certain color of the pixel on the texture in the fragment shader. And in Elm, this looks like this. So this is the whole encapsulation of the rendering pipeline. It's an entity function. So this is a type signature of it. You pass it a vertex shader, fragment shader, a mesh, and uniforms. And as a result, you get an entity type. And in order to see this entity on the screen, you use two HTML functions. You pass it a list of attributes that will be applied on the canvas element, so width or height, for example. And you pass it a list of entities that you want to see. And then you can plug it anywhere in your virtual DOM tree of Elm. So let's study the simplest possible example, also known as a hello world in the WebGL world, so an RGB triangle. So we will go through 3 simple steps. We will define mesh, implement shaders, and then wrap it up together into an entity. So in order to define a mesh, we first define your own custom attributes type. In our case, for each vertex, we want to store its position and a color. And then using WebGL triangles function, we pass it a list of tuples for each vertex. In our case, it's just one triangle that we want to see. So the next thing that we implement is a vertex shader. And here you can see GLSL code block. What you may also notice is that attribute, uniform, and varying definitions in the GLSL code exactly match the type signature that we define on for our shader. So if something is wrong, then this one wouldn't compile. So the output of this is the output of the vertex shader is position. We multiply rotation matrix with position of each vertex, and we also pass the color of the vertex to the fragment shader with varying. Fragment shader is very simple. It just takes the varying of the color and it sets it to color of the pixel on the screen. So wrapping it up, we just have a view function where, in our case, the model may be just a rotation angle. We call to HTML function, pass width and height for our canvas element, and then we render our entity and configure it with a rotation which is calculated using makeRotate function that is conveniently provided in the linear algebra package. So you just define an angle of rotation and an axis of rotation. So yeah, so what is left to do is you hook it with with animation frame subscription, and then this is what you're going to see. So yeah, this is as simple as it is, and now we will see what else is possible using the library. So as I said before, the reason why I chose WebGL is because I wanted to render the game, and the first challenge I had to overcome was to render something in 2D, because all examples online are using 3D. They are usually just cubes or this RGB triangle, and I wanted to render a sprite sheet with animation frames. So in this case, I just passed the texture as uniform and used it in the fragment shader, where I implemented some small code that did this whole lookup. So the challenges here were to get familiar with the clip space. It's a coordinate space of WebGL where every axis is from -1 to 1. And also the texture space. So looking up pixels on the texture, to do that you have to use a scale from 0 to 1, and you're not using the pixel scale of the texture. And the last challenge was to address issues with alpha transparency, but that was not hard. Another very nice example, because Elm is a functional language, so using recursion you can generate very nice meshes. So in this case, it shows rendering a sphere using recursion. So what you do, you start with a simple octahedron shape, and then you divide each triangle by 4 triangles, and then project the vertices back onto the surface of the sphere. So the more steps you take, the closer it will approximate the real sphere. And the next example, I'm going to play it for a little bit. So yeah, by the way, the whole presentation is written in Elm. So what you can see here is the actual Elm WebGL code running. So this is a snake game that was created by Thibaut. Is Thibaut here? Yeah, he should be in at this conference too. What we did together, we migrated it to WebGL step by step with multiple pull requests. So first we introduced flat lighting, and we also added simple planar shadows. So the way we implemented shadows was through creating a matrix that smashes the mesh onto the surface. And there are more games implemented in Elm using WebGL. So the 2 first games are the games that I contributed to. Elm Street 404 that we built at Zalando, which is like a traveling salesman problem where you deliver clothes from warehouses to people who want to buy clothes. And Moji is a platformer game implemented on 64 by 64 pixels grid. There are also games created by folks from Elm Community. Mage City is as an experiment to have some kind of RPG style where Andrey Kuzmin integrated it with a tiled map editor. So you can draw a map using the tool and then have it imported into your Elm code. And Into the Heavens, a game by Nick Holland, which is a 3D flight simulator. It uses an outdated version of Elm WebGL. However, the API didn't change dramatically, so it's still nice to follow. And since last year, there are more games created in Elm. Flappy Bird cloned by Andrey Kuzmin. There's a Countdown game, and a Rubiks Cube game that I worked on just recently. So we'll go in to see what were the challenges in implementing Rubiks Cube in Elm. So the challenges were mainly ray tracing, because you need to understand on which cell on the surface of the cube user clicks, and in order to do this, you're applying inverted matrices. You start with mouse coordinate, and then you calculate coordinate in the 3D space, and then you draw a ray from the camera towards this coordinate, and then you calculate, you find out which triangles this ray intersects with, and then you're able to tell which cell has been clicked. I also used something that is called quaternions, and this is a nicer way to model rotations in 3D. So this allowed me to implement transitions from one rotation back into the original rotation. And today I open sourced the game, so you can also check the source code of it and ask me any questions if you find. If you want to learn more shaders programming, there is a nice website called Shader Toy where many people publish their creative shaders. So I tried to run it using WebGL in Elm, and this was not hard. Mainly on this website, a mesh is just a rectangle made of two triangles, and the whole creativity, the whole implementation is in the fragment shader. So what I had to do is I had to wire subscriptions and pass them as uniforms, so that then this thing responds, for example, to mouse moves. So yeah, with very little code, I was able to adapt this famous shader by Alexander Alexeyev called Seascape. Another nice demo is rendering terrain by Dave Jeffrey, and the cool thing about this is that he used a texture as a height map. So texture was not used in the fragment shader, but it was used in the vertex shader, so that you define your mesh as a grid on the plane, and then using coordinates you can do a lookup on the texture to tell how high each vertex is. And he also used textures, of course, in the fragment shader, and the cool idea there was to use detailed texture and not detailed texture, and then fuse them depending on the distance from the camera. So the closer something is, more detailed it is. And also it has a skybox around the map. So stepping a bit into the future, there is also an OPS format support with, implemented by Florian Ziegler, where you can import a mesh created in Blender. So it supports a subset of waveform format. And for example, it supports normal maps and textures. for normal maps, you need them when you want your surface to reflect the light differently. So it's not looking smooth, but it's rather sharp. And I would like to show this. Sorry, this is... Probably clicked the wrong. There's a model viewer in here. You can see Elm logo, but it looks like bricks. And this is done by using normal maps. And the latest thing, the last thing that I wanted to show is SceneGraph package by Ian McKinsey, and this is probably the most amazing thing happening right now in Elm WebGL. So he implemented physically based rendering that supports multiple different light sources and also supports customizable materials. So you can make your objects look like metal or plastic. And I would like to show this too. So you can control material, you can make it look like copper or plastic. In this talk, I would like to thank John P. Mayer, who originally created this library, and I would also like to thank Evan Chaplicki, who helped me to come up with API for WebGL version 2. And thank you for being a great audience. So we can take questions now.
Yeah, I think we have time for about 5 questions, maybe more.
Thank you. Sorry. First, that's awesome. And I have a question about animation and interactivity. What would in more traditional approach be like a main loop when you're passing all the, I don't know, deltas around? I would imagine that in Elm you would do it slightly different, like change the geometry in certain, if it's an animation step by step, like how do you deal with that? It's probably not a part of Elm WebGL library. It's usually what you implement in application. How do you deal with it? Is it different from the usual approach?
So it's very similar to what you would do in Elm itself, as WebGL is only plugged into the view function, but the Elm architecture includes subscriptions, update function, and initial model, and there is animation frame subscription. So you subscribe to animation frames, and then you can receive time differences between frames, and then you use it in your update function to animate something, but then WebGL renders like declaratively computed things.
You mentioned there's a linear algebra library for this. Is that actually written in JavaScript? Because I usually assume that the linear algebra stuff needs to be like super fast.
So yeah, it has some native JavaScript code. It uses native type 64, 32 float arrays. It's I think it was originally created by Mozilla, and it just borrows some of the code for the native part.
Hi. I might be a duplicate for 2 questions ago. What happened? My question is regarding casual games or simpler animations. When you do a casual game, actually you're making, there are a couple of steps which are quite simpler in order to make it happen faster. What I mean, what he asked, animations, for example, you specify the animation and afterwards you don't want to bother about it. Even if you do that in the update loop as, I mean, regular game engines do that. So what are the possibilities for a actual game engine, a simpler game engine for casual games in Elm? Since, for example, WebSocket libraries, what they do is that they take their messages in the update loop and they handle them appropriately. They abstract, I mean, still you have control of the state and everything, but only on that part of the model they are handling their part. For example, for animations or resource loading or physics and 2D physics. 3D physics is a bit different. What are your thoughts on building such game engine? Is that like appropriate, plausible, and feasible? Because I tried Elm 08, I also forked it, tried to contribute it, but it doesn't have like much buzz about it. I mean, the developer left it, I guess. So what are your thoughts about it, and does Elm has community to go in that direction at all? To target casual game developers, to make a functional game?
So I guess this is what we have been trying so far. There is a game dev channel on the Elm Slack, and people there are quite active. So I'm building small games myself, and to show that things like this are possible. So you have WebSockets in Elm, or you know that, right? So you,
yeah.
Also, animation frame is something that you can subscribe to conditionally. So subscriptions is a function from model to list of subscriptions. What you can do there, you can check if you need to animate. If you need, then you return this subscription. If not, you don't return it, and then nothing is changing, nothing is animating. So actually I use this in the Rubiks Cube, for example. So I don't want to render 60 frames per second when nothing is happening on the screen, and I know for sure that nothing should happen. So also for optimizations, you can use lazy. So there is a function called html.lazy, and it checks if the model or an argument that you pass to it has not changed. Then the whole virtual DOM subtree will be not rendered. It will not be reevaluated even. So for example, if you want to detach keyboard configuration from animation, if you don't want keyboard to intervene and call another unnecessary render, you can store pressed keys outside, and then you have a submodel that stores the game, and you only update it when you receive animation frame subscription, and then you read the state of the keyboard from the outside, for example. So there are ways, and we are currently exploring them. I think what we need more is enthusiasts, or people who would be willing to build games, and then we will learn from each other and come up with solutions to various problems. Does it answer your question?
Yeah, I will join the channel, definitely. Thanks.
Thank you.
Hi. Down here. Hi. Max Algate from Chalmers. So you showed us these shaders, and you showed that the shader is written in some form of QDSL-like thing for GLSL. Could you talk about that choice of having a quoted DSL rather than having just an embedded DSL with code generation? What are the sort of, why go for the QDSL approach?
A shader is not a DSL, it's the real GLSL code.
Right, I mean, you have the quasi-quoted there, which are using to obviously embed the shader code into your application. What are the advantages you see with doing that in favor of just using an eDSL where you could program in a more familiar style, let's say?
So the reason why it is like this is it's a historical reason. So I probably don't have the influence over doing, like, changing it and making GLSL that DSL that would generate GLSL. There is some ongoing work. I tried to investigate how shaders are programmed elsewhere, and I saw that people are building kind of their own languages or their own graphs, or how is it called, that would generate a shader. And this is very interesting, and it's possible to explore this in Elm right now as well. There is a function called unsafe GLSL for the reason that it will give you a shader of any type. So you lose the type guarantees with that, but it takes a string, so you can build the string and you can build the shader yourself in order if you want to explore this realm.
Yeah, I was just going to comment back and say that the sort of the eDSL group at Chalmers, everyone would say that that's a backend problem. That's a library writer's problem. The goal is to provide an interface which is nicely typed, and then generating a string in the backend, well, you just have to get that right once, right?
So yeah, you can also hardcode shaders and then create a library like the project that Ian is working on, like the SceneGraph package, where you don't write shaders. You just have a way to configure material, and then the library will handle this for you. I guess.
Yeah, it takes a while for the mic to switch on. So let's give Andrey a round of applause and thank you one last time.
Thank you.